All right. Hi, everybody. Welcome to the dawn of the final week. The first, well, not like final week, but like final week before the AP test, the thing we've been building up to. So, yeah, it's exciting. So, kind of what we're doing today, I'm going to give it to you for Tuesday, Wednesday, and then Thursday, you'll take the AP test. So, kind of the last thing that we're doing in preparation of this AP test is to do a practice question that the College Board gave us that is kind of like what to expect, kind of, on the AP test. Pretty much what they did is they took an old question that they have and they kind of reformatted it a little bit to fit what we're going to see on the AP test. So I don't know if it's like super indicative of the format and the style, because again, they did just take an old test and they said, let's kind of mess with it a little bit. So I don't know if they mess with it in a super intentional way, or if they're just like, hey, this is a good question, we have it lying around. But regardless, it's one of these quantitative, qualitative type questions that we'll see. And yeah, we'll give it a go and kind of get used to that format and get used to how we're going to submit it on the AP test. So maybe Thursday, a couple days ago, I made a little video. I posted it on Google Classroom, and it was just like, hey, here's the format for the AP test. Here's what to expect, blah, 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 all that good stuff. So if you haven't seen that yet, if you're confused about anything going on, make sure to watch that. I didn't post it as an assignment. I just kind of posted it here in the stream as like AP test guide. So give it a look, give it a see. If you have any questions, let me know. Little life update, not really a life update, I don't know. That sounds like something big happened. Nothing big happened. On Wednesday, I'm planning on just kind of being available in Zoom for most of the day. So if you guys have any questions, last minute things to check with the AP test, I'll be around. So I'll kind of drop in that link and let you know. But yeah, so with this one, the format's a little bit weird just because I want to like simulate what it's like to take one of these tests. So what you'll see is you'll have like the page, you'll put in your e-ticket, all that good stuff, and you'll get the questions. And what the College Board wants us to do is kind of have your questions on one side, bring it over to the screen, and then on the other side, have your Google Doc where you type in your answers. So then you'll upload either a .docx or a PDF, just like you'll do in the AP test. So yeah, I'll just kind of go over this. This is kind of like the key slash the introduction to the lesson, apparently. But yeah, so you'll see in here, here's the link to it. I'll also link it like in the assignment. But yeah, so we have a good old circular motion and pendulum question, which is cool. I kind of like how they mix these up. And what I'm going to do is I'm actually going to pull up what I did. I kind of already did this because I didn't think it'd be really worth like you watching me type for a long time. So I have the questions pulled up over here. I don't know how to make this any bit smaller. If anybody's like a big OneNote person, let me know. But so I kind of have it like this. And I'm just going to show you that just so you have my work and kind of what I did to help me get to where I am at. And then a little reminder, you'll see it in the video, but when you're doing the AP test, they want you to have a header with your initials and then your AP ID number, and then you'll clearly label all the parts of your question. So again, I went ahead and did this, and I'll just kind of read through my responses. But so what we're saying is a small sphere of mass m is suspended by a string of length L. The sphere is made to move in a horizontal circle of radius r at a constant speed as shown above. The center of the circle is labeled point C, and the string makes angle theta naught with the vertical. Two students are discussing the motion of the sphere and make the following statements. Student 1, none of the forces exerted on the sphere are in the direction of point C, the center of the circular path. Therefore, I don't see how there can be a centripetal force exerted on the sphere to make it move in a circle. Student 2 says, I see another problem. The tension force exerted by the string is at an angle from the vertical. Therefore, its vertical component can be less than the weight mg of the sphere. That means that the net force on the sphere has a downwards vertical component, and the sphere should move downwards as well as moving around in a circle. Sorry, those colors are a little bit hard to read from a distance for me. So then part A, what is one aspect of student 1's reasoning that is incorrect? Explain why. This is nice, we just need one aspect. So again, like we did when we had these quantitative, qualitative type questions, is I just went through and I highlighted all of the statements that we could argue from. So kind of each separate statement, I would recommend just like in your mind saying this is a separate statement. You won't be able to highlight unless you really quickly like print out the test. But yeah, so kind of dictating, hey, this is one statement, this is another statement. I'm also going to move my candle because I don't know if you can hear it or not. So yeah. So I said, okay, we have two statements. The pink one, whatever, is more of an opinion. The blue one is more of a fact that the student is saying. So I said, none of the forces exerted on the sphere are in the direction of point C, the center of the circular path, is an incorrect aspect of student one's reasoning. So directly quote that reasoning. This is incorrect because there is a tension force acting on the sphere caused by the string. The string is at an angle. The tension force acts along strings and ropes. If the string is at an angle and facing towards point C, then there must be a tension force pointing towards point C. So I'm just kind of arguing from the fact tension acts along strings. There's a component of this string that is, if we kind of split it into vertical and horizontal, there's a horizontal component of the string, which means there has to be a horizontal component of tension. So just kind of arguing from how forces work and how tension works. So from like these universal truths is what we're going to argue from. For part B, we're saying, what is one aspect of student 2's reasoning that's incorrect? Explain why. So again, just kind of directly quoting, we have two things here that are incorrect. I believe that the yellow one and the orange one are pretty wrong. Yeah, the tension force is bad. The string is at an angle, that's true. But then yeah, the yellow one and the orange one are wrong. I just said that the yellow one is what I'm going to argue. I can pick either one. I think yellow is a little bit easier to argue. So which one's incorrect? Its vertical component must be less than the weight mg of the sphere is an incorrect aspect of student 2's reasoning. The problem statement says that the sphere is made to move in a horizontal circle of radius r. This means that the sphere is not moving upwards or downwards because it has the term horizontal in it. Because the sphere is not changing its velocity in the vertical direction, there is no net force in the vertical direction. Newton's first law states that objects accelerate in the direction of the net force. If the sphere is not moving downwards, then there's no net force downwards. So we have this idea it's not accelerating down, so there can't be a downwards net force. We have to have this balanced net force in the vertical direction. So we can't have the vertical component of tension be less than the weight, because then we would see a net downwards force and a net downwards acceleration. All right, so far not too bad. Student 3 correctly derives the equations F net equals Ft r over L and mg equals Ft square root L squared minus r squared over L to relate the tension force Ft to the net force F net and the other quantities. And then we're just explaining, hey, pick one of these equations and talk about how it either, how we can use it to challenge the claims. So I'm going to be honest, I'm not super happy with my answers for these ones, but we'll roll with it. I mean, it gets the job done, but I feel like it's kind of wordy. So I don't know, maybe you guys will come up with a better answer. I don't know, this one's kind of rough. But so yeah, we're saying for C, the equation mg equals ft times the square root of L squared minus r squared divided by L can be used to challenge student 1's claim. Student 1 states that none of the forces exerted on the sphere are in the direction of point C, the center of the circular path. The forces acting on the sphere are the weight force and the tension force that's acting at that angle. Because the sphere isn't accelerating in the vertical direction, the forces in the vertical direction are balanced. So Fg is equal to the vertical component of tension. Because the sphere isn't accelerating in the vertical direction, they're balanced. The weight force is balanced out by a component of the tension force, as stated in the equation. If the remaining tension force isn't balanced by the weight force, it must be acting in the horizontal direction. The horizontal direction is inwards towards point C, the center of the circular path. Because we have this tension component is less than Ft, there's a component that must be in the horizontal direction. So I kind of set up an argument saying, well, we have this balance in the y direction. The only other force has to be in the x direction if we're thinking in terms of components. Everything else in the y direction would interact with each other. So we're leaving an aspect in the horizontal direction, which is the same direction as the center point of the sphere. Because not all the tension is acting vertically, as said by this equation, some of it has to be pointing inwards. It has to be in the horizontal direction. And then D is the one that I'm more unhappy with. We're saying the equation mg equals ft square root L squared minus r squared over L can be used to challenge student 2's claim. Student 2 states that the vertical component must be less than the weight mg of the sphere. The equation states that mg is equal to the vertical component of the tension force. The equation is the vertical component of the tension force due to the Pythagorean theorem and the trigonometric identity of cosine. Mg equals ft cosine theta naught by analyzing the vertical component. Cosine theta is equal to adjacent over hypotenuse. The adjacent side is found by the Pythagorean theorem. R squared plus a squared equals L squared. A squared equals L squared minus R squared. A equals square root L squared minus R squared. The hypotenuse is L. This is an expression stating that the weight force equals the vertical component of tension. So pretty much I did the math and then I wrote about it. So yeah, this is a new format. They don't have like a key posted for this. I don't know what they expect. So yeah, I just kind of said, here's the math for it, and then I wrote about it. Just saying, hey, this is a component. This is just saying, yeah, the y component of tension is equal to mg here. And just saying, yes, this indeed, this weird thing, this ft times square root L squared minus R squared over L is just the vertical component of tension. So they argued, oh, it's less than it, and I just argued, no, it is equal to it. That was weird. Okay. The student observes that the radius r increases as the speed v of the sphere increases. Together, they derive the equation r equals v times square root L over g to calculate the radius of the circle r, followed by the sphere if its speed is v. Then for E, regardless of whether the equation is correct or incorrect, does it plausibly model the student's observation about the relationship between r and v? Why or why not? So first things first, we have to identify what that relationship is. They're saying as r increases, the speed v of the sphere increases. So we have r goes up, v goes up, and we just have to see, would that happen with this equation? And we see, yeah, it would. So I said yes. The student states that as r increases, the speed v of the sphere increases. In the equation, r is directly related to v. We have r is equal to v times square root of L over g. So square root L over g is really just the slope, and we have this direct proportionality if we were graphing r versus v. So yeah, they're directly proportional to each other, which means if r goes up, then v is going to go up proportionally. And then this equation does not correctly model the relationship between r and v. If v is very fast, explain why. So we have to kind of think about our limiting cases here. What would actually happen? So we know if these things sped up, we'd kind of see that the sphere would start to, right, it would start to kind of spin so that r would go up. It would start to kind of increase in that height. It would go from, okay, like if we had no speed, it would be just hanging here and then increasing. And what we know is, well, r can't increase infinitely. So for this case, we'll say, okay, theoretically, v can keep on going until it reaches the speed of light, but it's not going to reach that fast. But it's going to go really, it can be really, really fast. V can increase a bunch, but r is very limited by what it can increase by, because r is really only limited by the length of the spring, or the string. The maximum that r can be is going to be the length L, right? We can't have it go, okay, we're at this maximum height where L is pretty much the radius. We can't go further than that. We can't like make our string longer. Our string is a set length. So we're saying theoretically v could increase until it reaches the speed of light. R, however, cannot increase without a bound. The highest value that r can be is the length of the string. If v is very fast, it can increase to any value, but r is limited by L and will eventually not be able to increase anymore. All right. Instead of moving in a horizontal circle, the sphere now moves in a vertical plane so that it is a simple pendulum as shown above. The maximum angle theta max that the string makes from the vertical can be assumed to be small. The graph below shows data for the square of the pendulum period t as a function of string length L. So we're just looking, okay, we have t squared versus L. And we know that pretty much, we'll get to in a second, but we have this equation for the period of a pendulum that says t is equal to 2 pi square root of L over g. And we're graphing t squared versus L, so let's just make that t squared versus L. So if we square both sides, we get t squared equals 4 pi squared L over g, and we're really graphing this situation where we have t squared equals 4 pi squared over g times L. So if we're looking at this, t squared, that's on our y-axis, that's okay, and then L is on our horizontal axis. So we've linearized this. We have this linear equation where 4 pi squared over g is just equal to the slope. So let's check these situations out now. For g, it's saying, okay, what happens if we increase the mass of the sphere? So for g, we can say the graph won't change. The sphere on a string, I wrote spring, but I meant string. Sphere on a string is modeled by a pendulum. The equation for the period of a pendulum has no dependence on the mass of the sphere. The equation is Ts equals 2 pi times square root L over g, which does not change as mass changes. If we square both sides, the equation becomes t squared equals 4 pi squared times L divided by g. Changing m has no effect on this equation and no effect on our graph, because we're really just graphing that where 4 pi squared over g is the slope. Same thing for h, the graph won't change. The sphere on the string is modeled by a pendulum. The equation for period of a pendulum has no dependence on the angle at low angles. So we see same exact reasoning. It doesn't show up. The amplitude doesn't affect anything. It doesn't show up in our equation at small angles. Then I, the pendulum is taken to the moon. So let's talk about like physical truths. What would happen if we took it to the moon? Moving the pendulum to the moon will decrease the slope of the graph. The gravitational field strength G on the moon is less than that of Earth. So we're saying, okay, G decreased. Here we are analyzing a graph of t squared versus L. The equation of the period of a pendulum is t squared equals 2 pi times the square root of L over g. If we square both sides, we end up with t squared equals 4 pi squared L over g. If we move this around a little bit, we get t squared equals 4 pi squared over g times L. So the slope of our graph of t squared versus L is just going to be 4 pi squared over g. And we see if g goes down, the slope is going to go down because that 4 pi squared over g quantity, that's going to be our slope. And I think that actually means the slope will increase, right? Because g is on the bottom. So if we have a lower denominator, that will actually increase. So that should be, pretend that all said increase. Increase, whatever you want. Variable increase. All right, that's my bad. Should I redo that? No, I'm not going to redo it. No, we're good. Okay, we're good. All right, with J, this is another one that I'm unhappy with, but again, they didn't provide a key, so we'll see what happens. The graph above shows the angle theta from the vertical as a function of time for the pendulum. Explain how this graph shows evidence of a net force acting on the sphere and how it shows that this net force is a restoring force. So my answer is fine, but I think it's a little bit long-winded. So what we're saying here is the graph of angle theta versus t can be thought of as a graph of angular displacement versus time, so that theta versus t. So we're thinking like angular variables. The slope of angular displacement versus time shows the angular velocity versus time, or just angular velocity. Slope is going to be angular velocity, just how like displacement versus time, the slope is velocity. So therefore, if the slope is changing, so the angular velocity is changing, that means that we have an angular acceleration. If we have an angular acceleration, that means we have an acceleration because a is equal to angular acceleration times r. Therefore, if there's an angular acceleration, there must be an acceleration. If there's an acceleration, there must be a net force by Newton's second law, F equals ma. So this is a restoring force because when the angular displacement is at a positive at time t equals 0, the slope of the graph is going from 0 to a more negative number. This shows that the acceleration is negative at a maximum displacement. Therefore, the net force is opposite the direction of the displacement. This is indicative of a restoring force. So pretty much we just have this idea. At a positive, at our maximum angle, we see, oh, well, our slope is getting more negative, which means that we have this negative acceleration. So as our displacement is positive, our acceleration is negative and vice versa. Down here, when we have this negative displacement, our acceleration is becoming more positive. So our acceleration is acting in the opposite direction, or sorry, our force, we should say, is acting in the opposite direction of our displacement, which means that we have a restoring force. It's going to bring us back to equilibrium. All right. And the last one, I think this is a very weirdly worded question. As the sphere swings back and forth, it also rotates a small amount during each swing. The figure below indicates the direction that the sphere rotates as it is swinging in each direction. In order for the sphere's rotation to change direction, a torque must be exerted on the sphere. When the sphere is at its maximum, rightwards displacement, what is the direction, clockwise or counterclockwise, of the torque exerted on the sphere with respect to the point of attachment between the sphere and the string? Briefly state why the torque is in the direction you indicated. So this one, it's weird. It's worded very weirdly, but pretty much what it's saying is when it moves to the right, it's spinning in the counterclockwise direction. When it moves to the left, it's spinning in the clockwise direction. That's really all that we need. So what we're saying here is, well, the torque has to be in the clockwise direction then. When it's going to the right, we have to have a torque that's in the clockwise direction because as the sphere swings to its maximum rightwards displacement, it is spinning in the counterclockwise direction. As the sphere swings from right to left, it is spinning in the clockwise direction. In order to change directions, the sphere must stop and then start spinning in the clockwise direction. The only way to stop its counterclockwise rotation is to have a torque in the clockwise direction, providing its angular acceleration in the clockwise direction. So pretty much, it's spinning in the counterclockwise direction. It has to stop and then start spinning clockwise when it's going in the other direction. So in order for it to stop, come to rest, and then start going the other way, it has to be acting against it. It can't be working with it. If we had a torque that was making it spin more counterclockwise, it would keep on spinning counterclockwise. It would never stop and then change directions like we see here. So yeah, that's those ones. Let me know if you have any questions. Again, they didn't provide a key for this. Like none of this I don't think is like wrong, but the wordiness. I feel like I made it kind of wordy, but hopefully they're okay explanations. So yeah, let me know if you have any questions. And yeah, that's kind of it. So yeah.